Good morning and welcome back. Today we will talk about plasma physics 21.526. We will talk about page 54 to 83. We will complete chapter 6 and chapter 7 as well in Nicholson. Okay, so we will start with, we will discuss magnetized plasma. But before we start, I would like to briefly review what we have learned so far. So go back to here. Go back to the very beginning. Maybe here. We discussed the linear velocity equations. So change to laser pointer. Okay, this is the linear velocity equations. Linearized velocity equation. So distribution function is related to here and here. And we have another one. From these two, we can calculate everything. So first, let's assume J and E. J and E has a simple relation we call conductivity tensor. So next page shows that J1K is related to here. But J can also be obtained from the distribution function, from velocity equations. So J can calculate. So here we have a simple relation using equation 125 and substitute dispersion, the relation between J and E. So we can rewrite this equation into this form. That's equation 146. But what is conductivity tensor? Here, conductivity tensor can be estimated easily from a particle dynamics. That means you need to know the particle's trajectory. Trajectory is easy, just here. That's zero order trajectory, unperturbed trajectory under magnetic field B0. Under magnetic field B0. Okay, so we can obtain this equation. Okay, so with this one, substitute everything. Eventually, we got all the coefficients. That's the, for example, we got all the coefficients. To obtain the conductivity tensor, we have to use this one. Okay, so for J1KX, we just use this one. We can obtain sigma xx, sigma sy, and sigma xz. Sigma xx is shown here. Others can be obtained using the similar techniques. So sigma xx is shown here. dxx is shown here. Together with sigma xx, dxy is equivalent to 4 pi I over w times sigma xy. So dxy is here. dxg is here. dyx equals d minus dxy. Okay, so eventually we have all the components. Okay, so the idea is easy. J is related through E through the conductivity tensor, and J is also related through distribution function. So conductivity tensor plus the distribution function, we can rewrite it into a tensor called D, a tensor called D. And to make sure EX, EY, EZ, the component to be non-zero, so only solution will be the determinant must be zero. So first, let's assume the wave is propagating in a z direction, same as magnetic field. So we can calculate all the coefficients, and eventually, by doing so, we have these relations. That the solution is easy. First, dZz equals 0, which will give us electrostatic wave. Second is this one equals 0. The parenthesis equals 0, which will give us the left-hand circularly polarized wave and right-hand circularly polarized wave. So the first one is relatively easy. That's electrostatic wave. We discussed electrostatic wave over and over again. So the solution is quite similar. Eventually, we got these solutions. That's electrostatic wave, which agree with electrostatic dispersion relations for an unmagnetized plasma. It's not surprised the magnetic field plays no role here because of this one. Okay, so for electrostatic wave with magnetic field or without magnetic field, the dispersion relation is the same. How about electromagnetic waves? Electromagnetic wave, we have two parts, this one, and these two relations differ by a I here. So the first one is E1kx. Just rewrite these equations. And we know perpendicular component is 0. So the wave is propagating along the magnetic field. So other components is 0. Therefore, the determinant is simple. It's here, okay? So the coefficient is very easy, just this one. However, we know dxx equals I dxy. So there is a I here. On the other hand, this one can be substituted to here. There is a dxx. There is another I. So x component and y component differ by imaginary components. Okay, so imaginary components as shown here, equation 198 and 199. These two waves just represent a circularly polarized wave. Okay, so we have a circularly polarized wave. It could be right-hand circularly polarized or left-hand circularly polarized. Okay, and from left equations, we can further consider the simplest case. The simplest case here, just electrons only. Okay, if we consider both electrons and ion, what will happen? Both electrons and ion, we should write the equation like this one. Comprised of ion, electron cyclotron frequency, ion cyclotron frequency, electron plasma frequency, ion plasma frequency. That's different. Density may be the same, but plasma frequency will be different here. Okay, so from these two equations, we can solve many rules. For example, for the right-hand circularly polarized wave, we have two branches, 1, 2. For the left-hand circularly polarized wave, we have another 2 branches, dashed line, 1, 2. Okay. Last time we talked about high frequency solution here. That's high frequency electromagnetic wave. High frequency electromagnetic wave. And we also talk about an interesting phenomenon called Faraday rotation. Faraday rotation. Okay, that's Faraday's law. And we also talk about the Whistler wave. Whistler wave, intermediate frequency. Intermediate frequency, Whistler wave and electron cyclotron wave. Electron cyclotron wave here. Whistler wave, electron cyclotron frequency. Okay. And today we will continue our discussion by consider lower frequency electromagnetic wave. That's often wave, and ion cyclotron frequency. So in this region is often wave, and here is ion cyclotron frequency, omega I, that's omega E. Electron cyclotron frequency and ion cyclotron frequency. Actually, electron cyclotron frequency here. Ion cyclotron frequency is here. Okay. And just like a previous case, the frequency is relatively lower than ion cyclotron frequency. Just ion cyclotron frequency is here, and we just consider these regions. Low frequency. Okay, so omega is much lower than this one. Therefore, these relations can be rewritten into this form. Okay, substituting equation. These two equations into 111 and 211 and 212, we get the same result. Okay, but here, because this one is relatively small, so these terms will be much more important than this term. We can drop these terms. We can neglect the electron terms and get this one. Omega. So, and this is the, as you can see here, Mi cancel with this one. Therefore, we have Ni0, Mi here. So from these two, we know one is Me, the other is Mi. Therefore, this term is much more important than this one. Maybe because Me is relatively small. Me is relatively small compared with Mi. Okay, so we can equation 219 is the equation we are looking for. So we can define a velocity called orphan speed. Here, we can define a velocity called orphan speed. The orphan speed. Let me show you. Okay, maybe I should use mouse. click. Often wave, often speed. Often wave is a Swedish Nobel Prize. Swedish. He wins the Nobel Prize in physics in 1970. Okay, often speed and often wave is related here. We just define often speed here. Ni0mi is defined as rho I. So it's the mass density, 质量密度, often is an ion mass density. So the dispersion relation of the often wave, one more time, is shown here. Okay, c squared over VA squared. Go back to the previous case. This one is combined with this one. Cancel. So we have only one rho I here. Rho 4 pi rho I C squared over B0 squared. So we define C0 squared over B0 squared. So we can define this one. Okay, omega, we can group the omega square. So eventually we got these relations. Often wave is a proportional constant. Therefore, omega is proportional to Kz here with a proportional constant. Okay, VA over 1 plus VA squared over C squared. The proportional constant is here. Square root of this one. Okay, the proportional constant is here. So it's an often wave. Let me read it again. It just looks like a linear wave here. In this region is omega and Kz has a very simple relations. Very simple relations. But it's not the speed of light. It's much smaller. And it's related to the ion speed. So it's relatively small, as we shown here, relatively small. So the physics of the often wave is shown here. If we have a solenoid, just like this one, we have a solenoid here, and we can generate magnetic field. We can generate the magnetic field. And the magnetic field with flux is shown here. B field line, a solenoid here, and a uniform electron distribution here. What will happen? It looks like we will have some magnetic pressure force density here, greater than B squared, and magnetic tension force density as if the curve of B lines tends to become a straight line. So here you can see here, the B line tends to become a straight line. There is a force density and magnetic tension force here. So we have two force per unit volume. Okay, that's called force density here. The magnetic force density, force per unit volume. Okay, we first derived the useful concept of magnetic pressure. This is magnetic pressure here. And magnetic tension. 磁的就是要怎么说？张量不是tension。这个是磁压， 磁力线靠太近，它就会有彼此互相排斥的力量。那磁力线如果弯曲的，它就会想办法把它给拉直。Okay, return to the orphan wave. Since the two lower branch merged at omega smaller than omega I. One more time. Go back to this one. These two branches merged here, merged in this region. Okay. So the left hand and right hand circularly polarized wave have the same phase velocity and group velocity as well. So the linear polarized wave will remain a linear polarization, no difference. A linear polarized wave remain the same, no Faraday rotation, unlike the previous case. The figure below shows a linearly polarized wave with B1 in the y direction. B1, we have X, Y. G, that's Z direction, that's Y direction. A linear polarized wave with B1 in the Y direction. So B1 in the Y direction is AC field. And E1, of course, will be in the X directions. And the wave propagating in the G directions. Since omega smaller than omega I and omega E, the electron ion behavior can be described as E cross B drift. And B1 is too small, so E1 cross B0 drift. E1 drift, what is the direction? B0 in the Z direction. So that will be the same direction as the drift in B1. Okay, so that looks like it's a drift, E cross B drift. It looks like the behavior will be the plasma move together as if the field line changed. The superpose of B0 and B1 is shown here. Superpose of B0 and B1. So the magnetic field move as in the E cross B drift. So it looks like the plasma is frozen. The field line is frozen. The magnetic field line was frozen to the plasma. Or the plasma is frozen to the field line, the same. They have the same response, same behavior. Same response or same behavior. So therefore, they have frozen together. Another case. On the other hand, when the magnetic field lines are bent, they is the tension force. What is the tension force here? 当磁力线被弯曲的，它就有个力量想把它拉直，拉直就会产生一个力，那产生一个restoring force to drive the plasma back to drive the plasma back, so that the field lines become straight. 要把磁力线给拉直，再度拉直。As the field lines are straightened, the momentum of plasma carries the field line further back. 因为要把它拉直会有点超过 thus the bending the field line again in the opposite direction. 哇，过犹不及。那像这个要把它拉回来又产生过头了。The tension force then acts again to start another oscillation. 所以这个东西就会在这边摆荡，所以它就会好像整个 orphan wave。它就好像锁住 plasma 会 move， 好像一起动。Note that we have assumed 我们假设这个东西 hence all quantity vary with the z variable. This implies that at a given time, this one drift, E cross B drift in the y direction has the same speed at all points along y. 就在 y 的这个方向，大家是一起移动的，因为它根本不 depends on y 啊，它 depends on z only 啊。Okay, thus the drift motion will not compress or decompress. 所以这个 E cross B drift 根本就不会影响到 plasma density variation 一样，它只是会晃动，但是它不会压迫或者是挤压，或者是不挤压。The plasma remain uniform， 一样是均匀的。In the process， 在这个过程中 ，often wave 的过程中，它根本就是 uniform 的。OK， 所以这是一个很有趣的现象。Often wave. We have another alternative derivation of the often wave. So maybe you can derive the often wave by yourself. Here is a simplified version. We start with E cross B drift. Okay. So this page you can derive by yourself. A simple derivation, not starts from the velocity equation, but starts from here. Simple derivation, you can prove the often wave, the behavior of the often wave. Okay, these two pages. So eventually we have these relations. Simple derivation from the fluid equation, chapter 7. Okay, now let's consider another case. That's the wave propagating perpendicular to B0 to here, perpendicular. Okay, unlike the previous case. In the previous case, we have electron-cyclone wave. We have left-hand circularly polarized, right-hand circularly polarized. We have many equations. We have many waves. Right-hand circularly polarized, left circularly polarized, electron-cyclone frequency, and Whistler wave, often wave, ion cyclone wave. Yeah. Now let's consider another case. Here, K is K perpendicular, and it can be in X direction or Y direction, okay? But anyway, let's assume it's isotropic distribution here. And then we have these relations because they are the same. With Kz equals 0, so we can simplify okay, and factoring out the G integration. Factoring out the G integration because of axisymmetry. So if we perform the integration, this one will become symmetric. So this part will be 0. Factoring out the BZ integration from 226 and 227, we have another good information. 0 again. Okay? It's an even function of BZ. Same argument. Even function of BZ. Even function of BZ. Therefore, with the Z component will be 0. So we have 4 components, 9 components. Among them, 4 are 0. 1, 2, 3, 4. Lucky, we we can reduce our calculation into this form. And the component is shown here. The component dxs, dxy, dyx, dyyy, and dzz. Okay, quite similar, quite similar. Okay, very similar to our previous study, except here, except the integration here, except here, except here. Okay, using equation, and what's next? Next step is to assume a cold plasma. For example, we assume a cold plasma and we obtain a simple relations. Okay, so by substituting a cold plasma, we got this one, and others is shown here. We don't have to, just like previous case, we have a big picture, not a small picture. According to my experience, the students, no matter where he's from, always has the ability to derive this equation by themselves, provided that we give him an example. And then they have the ability to derive this equation by themselves. Okay, using equation, once again, we have this one, and okay, and this one. DZZ is shown here, and others are shown here. This determinant is 0. Note that we have assumed K is in Kx, and Kz equals 0. So K just propagate in the Z direction, as shown in the X direction, and magnetic field is in the Z direction. Okay, as wave is perpendicular to the magnetic field, zero order magnetic field. This explains why dxs and dsy are unequal. Although the system is isotropic in x and y, but dxs and dxy is unequal. Okay, it's unequal. So first, let's consider the simplest case. That is dzz equals 0. So we have the ordinary mode, 正常的 ordinary mode. That means dzz equals these relations. For electron, their plasma frequency is much, much higher than the ion frequency. So we can neglect the ion contribution. So we just consider the plasma frequency. We already learned this one before, with or without the magnetic field. This one is the same. This is the ordinary mode, 正常的 ordinary mode. The ordinary mode is a pure electromagnetic mode, while the propagating in the direction perpendicular to the magnetic field, with the electric field parallel to B0EZ. Okay. The dispersion relation, this one, dispersion relation has the same form as that of the EM wave in an unmagnetized plasma. So the magnetized plasma and unmagnetized plasma has the same form, exactly the same. That's called ordinary mode. Ordinary mode. Okay. That's called ordinary mode. And the existence of magnetic field is unaffected by the external magnetic field. Okay, the electron motion is completely unaffected because electron can accelerate in the z direction. So Vx cross B0 Ez, Vz will give us no effect. So Lorentz force plays no role. It do not affect. It's unaffected by the external magnetic field. Unaffected. Let me use an eraser to erase this part. Okay. Next page. The general property, another case. The general property, okay. This one. The general property of dxx, dyy, and dxy. Rewrite the field equation here. So we got this one. Let's give the following information about the modes in equation 242. First, E1 equals this one of this mode lies on the xy plane. So wave is here propagating in the x direction, and field is in the ex, ey. So we have ex and ey. Under equation 242, either equation gives this one. From these two, we have dxs is real and dxy is imaginary. Last, dxx, these two are different by a factor I, implying that E1x and E1y are 90 degrees out of phase. Very similar to the previous case, but this time E1s and E1y are not less simple. They might differ by I, but the value is not 1. The ratio is not 1. Okay, so therefore, because of axisymmetry, therefore, E1 is elliptical polarized. If they are the same, they will be circularly polarized. If the amplitude are the same and phase differ by 90 degrees, they can be circularly polarized, left circularly polarized, or right circularly polarized. But this time, Ex and Ey are different. The amplitude 1kx, E1ky is unequal. Therefore, they form elliptical polarized 椭圆极化 elliptically polarized ELLIPTICALLY elliptically polarized. As shown in the figure, E1 is in X component and Y component. K is in the X component. Thus, in general, these modes are neither electrostatic. Electrostatic, we have this one. No electromagnetic. That's the plane wave. That's the plane wave. That means the wave propagating in this direction, and E cross B. not here. E field, B field, and that's pointing vector, or K field with number. Okay, so it's a E cross B, E cross B, E cross B here. Okay, actually E cross H. Okay, so it's not perfect. It's not a plane wave, but still, for me, I think it's still EM wave. I will define this one as EM wave, personally. OK， 我会认为这个还是电磁波，只不过它不是最简单的平面波，原因是在这个地方而已。OK， and the wave number is set at particular frequency. OK, consider, for example, the relative amplitude, 相对的振幅 their relation is here. If for some omega and k perpendicular, we can derive dx as equals 0. 那这个是 0 的话，代表说 E1k 会变得很大。And the mole will become electrostatic. OK? 哦，那就变成 once again 变成 electrostatic again. 或者是 another extreme, dxy equals 0 at some omega and k perpendicular. Then E1 就只有一个项，因为 E1k x component is 0, and the moles become electromagnetic because the wave propagating in x direction and E field is in a y direction. Okay, so it becomes electromagnetic. In either way, 不管怎么样，不管在这两个 case, E1 also becomes a linearly polarized 线性极化。这个是副词，这个是形容这个 linearly polarized. Okay, so I will stop for maybe 10 minutes, and we have a part B. You can study by yourself. Take a few minutes break. Okay, that's the end of the upper half.